All right, let's talk about the magic inside pretty much all of our devices. Semiconductors. They power literally everything. But how do they actually work? How do they create the electrical current that makes our digital world go round? Well, let's break it down.
So let's just jump right in with the big question. How in the world does something like silicon, the stuff our computer chips are made of, get electricity to flow? I mean, it's not a simple wire like copper. And that difference, that little bit of complexity, that's its superpower.
Okay, so here's the secret. A semiconductor is kind of like it has a split personality. See, it's not a great conductor. It won't just let electricity flow freely. But it's also not a great insulator, which would block it completely. It lives in this perfect sweet spot right in the middle. And its real power is that we can nudge it one way or the other.
To really get this, we have to start at the coldest place imaginable, absolute zero. Imagine a pure silicon crystal at this temperature. It's basically a perfect insulator. Why? Because all its electrons are totally locked down in what we call the valence band. They're stuck to their atoms, they can't move, and if electrons can't move, you get no current. It's totally stable and, honestly, pretty boring.
But this is where things get really cool. We don't have to do much to wake it up. All it takes is a little bit of energy. We're not talking about a lightning bolt here. Just the normal, everyday heat in a room is enough to unlock its potential. This is where the magic really starts. All right, check this out. On the left, you've got our frozen, boring atom at absolute zero. But look over on the right. This is what happens when we just warm it up a bit. That heat energy gives one of those locked-in electrons just enough of a kick to break free from its bond. It makes this incredible leap across an energy gap and lands in a higher energy level called the conduction band. And just like that, it's a free electron. It's ready to move. And that one action creates the most important thing in this whole story, the electron-hole pair. When that electron jumps up to the conduction band, it leaves behind a little vacancy. And this isn't just nothingness. This little spot acts like a particle with a positive charge. We call it a hole. So now we have our dynamic duo, the free electron and the hole. These two are the fundamental units of charge we're going to be working with. So we've got our two main characters on the stage now. We've got the negatively charged electron just zipping around freely in the conduction band, and we have the positively charged hole hanging out back in the valence band. Let's dig into what makes them tick.
So let's just run through that creation process one more time, step by step. First, the silicon crystal soaks up some heat. That energy lets a few valence electrons break their bonds and leap up into the conduction band. These guys are now our conduction electrons, and they've got a negative charge. And the super important part, for every single electron that makes that jump, a positively charged hole is created right where it used to be. And you gotta understand, this isn't something that happens once and then it's done. Nope, it's happening constantly. It's a super dynamic environment inside that crystal. Heat is always creating new electron hole pairs, and at the same time, other free electrons are running out of steam and falling back into empty holes. That's called recombination. The whole thing is just buzzing with activity. This constant buzzing gives us a really clear comparison. So the conduction electron, right, it's negative, it's hanging out in the high-energy conduction band, and it's totally free to move around. The hole is its mirror opposite. It's positive, it's down in the lower energy valence band, and, now this is a really key detail, it only seems to move. We'll get to exactly what that means in just a second. Okay, so this raises a pretty big question, right? We've got all these charged particles, electrons and holes buzzing around, but it's all random, it's total chaos. For any of this to be useful for us to get an actual current, we need to get them all marching in the same direction. So how do we do that? And the answer is we apply a voltage. That's the secret sauce. Think of voltage as the choreographer of this whole electrical dance. It creates an electric field that acts like a director, shouting out instructions, telling all those randomly moving charges which way to go. It turns the chaos into a clean, organized flow. And this is where having two types of charge carriers gets so incredibly important. Because the total current in a semiconductor isn't just one thing. It's actually the sum of two different currents happening at the exact same time. You've got the electron current and you've got the hole current. Let's start with the one that's easier to wrap your head around, electron current. This is just our free electrons, the ones up in the conduction band. They have a negative charge, so it's simple physics. When we apply voltage, they're pulled toward the positive terminal. It's a pretty straightforward flow of negative charge. And here you can see it happening. As soon as we apply that voltage, see the positive side is on the right, all those free-floating negative electrons stop their random dance and start drifting in a very organized way towards it. That collective movement, that drift, that is the electron current. Okay, but what about the holes? This is the mind-bending part. The holes themselves can't just pick up and move. Instead, an electron from a neighboring atom can jump into a nearby hole. But when it does that, guess what? It leaves a new hole where it just was. Think of it like a full parking lot with one empty space. A car moves into the empty space. Well, the car moved, but the empty space also just moved to where the car used to be. That apparent movement of the positive empty space, that's the whole current.
So why does any of this duality matter? Why is having two kinds of carriers so special? This is it, the grand finale. This is where we see the real genius behind how a semiconductor works. Okay, now here is the absolute knockout punch. The negative electrons, they move toward the positive terminal. The positive holes, they appear to move toward the negative terminal. They are flowing in opposite directions. But, and this is the beautiful part, because their charges are also opposite, these two opposite movements both contribute to the total current. They add together to create a bigger, more robust current. It's incredible. And for anyone who's ever looked at a circuit diagram, this explains a classic convention. We always draw conventional current as flowing from positive to negative. And you might think, wait, but electrons are negative and flow to the positive. And you're right. But that convention, that rule of thumb, is based on the direction of the whole current, the flow of positive charge. So now you know why. So let's just boil this all down. What did we learn? 1. Semiconductors need a little energy, like heat, to even create charge carriers. 2. They have two types of carriers, negative electrons and positive holes. 3. When you apply a voltage, you get two currents for the price of one, an electron current and a hole current. And 4. This unique dual carrier system is what makes these materials so unbelievably versatile. So we figured out how a pure semiconductor works, but it leaves a little bit up to chance, right? So here's a final thought to leave you with. What if we could control this? What if we could rig the game so that we always have way more electrons than holes, or way more holes than electrons? Well, turns out we can, and that process is the next chapter in this story. But that's a tale for another explainer. Thanks for tuning in.